Hi, in this video I will share the Indira Gandhi University MCA Data Structures and Algorithms previous questions solved. The first question is, what are sparse matrices? Explain with examples. A matrix can be defined as a two-dimensional array having m rows and n columns. A matrix with m rows and n columns is called m times n matrix. It is a set of numbers that are arranged in the horizontal or vertical lines of entries. The graphical representation of matrix is as follows as. Sparse matrices are those matrices that have the majority of their elements equal to 0. In other words, the sparse matrix can be defined as the matrix that has a greater number of 0 elements than the non-zero elements. Benefits of using the sparse matrix. Storage. We know that a sparse matrix contains lesser non-zero elements than 0, so less memory can be used to store elements. It evaluates only the non-zero elements. Computing time. In the case of searching in sparse matrix, we need to traverse only the non-zero elements rather than traversing all the sparse matrix elements. It saves computing time by logically designing a data structure traversing non-zero elements. Representation of sparse matrix. The non-zero elements in the sparse matrix can be stored using triplets that are rows, columns, and values. There are two ways to represent the sparse matrix that are listed as follows. They are array representation and linked list representation. Array representation of the sparse matrix. Representing a sparse matrix by a 2D array leads to the wastage of lots of memory. This is because zeros in the matrix are of no use, so storing zeros with non-zero elements is wastage of memory. To avoid such wastage, we can store only non-zero elements. If we store only non-zero elements, it reduces the traversal time and the storage space. In the 2D array representation of a sparse matrix, there are three fields used that are named -row. It is the index of a row where a non-zero element is located in the matrix. Column. It is the index of the column where a non-zero element is located in the matrix. Value. It is the value of the non-zero element that is located at the index, row, column. Let's understand the array representation of a sparse matrix with the help of the example given below. Consider the sparse matrix. In the above figure, we can observe a 5 by 4 sparse matrix containing 7 non-zero elements and 13 zero elements. The above matrix occupies 5 by 4 equals 20 memory space. Increasing the size of matrix will increase the wastage space. The tabular representation of the above matrix is given below. In the above structure, first column represents the rows, the second column represents the columns, and the third column represents the non-zero value. The first row of the table represents the triplets. The first triplet represents that the value 4 is stored at 0th row and first column. Similarly, the second triplet represents that the value 5 is stored at the 0th row and third column. In a similar manner, all triplets represent the stored location of the non-zero elements in the matrix. The programmatic representation is as follows as. Linked list representation of the sparse matrix. In a linked list representation, the linked list data structure is used to represent the sparse matrix. The advantage of using a linked list to represent the sparse matrix is that the complexity of inserting or deleting a node in a linked list is lesser than the array. Unlike the array representation, a node in the linked list representation consists of 4 fields. The 4 fields of the linked list are given as follows. Row. It represents the index of the row where the non-zero element is located. Column. It represents the index of the column where the non-zero element is located. Value. It is the value of the non-zero element that is located at the index, row, column. Next node. It stores the address of the next node. The node structure of the linked list representation of the sparse matrix is shown in the below image. Let's understand the linked list representation of sparse matrix with the help of the example given below. Consider the sparse matrix. In the above figure, we can observe a 4x4 sparse matrix containing 5 non-zero elements and 11 zero elements. Above matrix occupies 4x4 equals 16 memory space. Increasing the size of matrix will increase the wastage space. The linked list representation of the above matrix is given below.